So let's consider the possibility that I am going to break the critical path here. And breaking the critical path essentially, as far as I am concerned, involves introducing a register. Okay. Now comes the question, is this sufficient? Can I just do whatever I have done now, which is breaking this path between E and C, right? If I do not change anything else and just introduce one register over there, I am changing the functionality of my entire circuit, right? If you think in terms of a transfer function, the output transfer function will change. It will no longer be what I expected it to be. It will not just be a sort of delayed version of the input or of the expected output. It will have completely different characteristics. Okay. If I do not want this to happen, what should I do? I need to also make sure that all the paths which are leading from A to D have the same amount of delay on them. Okay. There are multiple ways of doing this, right. So, what would be the obvious one? Also introduce delays on B, C and E, F, right. So, this for example would solve the problem for me, right. If I also introduce registers here and here, now what I get is my critical path effectively becomes this. Just to sort of take a slightly different approach on this, let us also redraw this slightly and say what happens if I had chosen a slightly different way in which to do the partitioning. In other words, I decided to go ahead and put a register over here, that is fine. Okay. I could also have chosen to partition here, in other words put a register between A and B and between E and F. Okay. In other words, all that I am saying is this is a valid pipelining transformation. Will this solve my problem? Not really, because what will happen over here is I will end up getting the slightly longer critical path over here. Okay. But this is still a valid pipelining. On the other hand, something like this, right, where I essentially say I would introduce a register here and a register here, right. This is okay from a critical path point of view, right, because after all the critical path now has essentially become this or this, both of them are equal to 3, right. But there is a problem, right, and the problem is simply that what I did over here is invalid, right. How do I understand exactly the problem that I have over here? You can look at it like this. Effectively, if I redraw this, right, and I just put A, B and C, which are all the nodes on one side of my pipelining, right, versus D, E and F over here, right. What are the edges that I have? I have an edge from A to B, one from B to C. There is one edge which has been cut from A to E, that is fine. There is also something going from E to C, okay, something from C to F and from C to D. Okay. So, actually speaking, I mean, so the problem is not really on the C to F node, the problem is on the C to E node that I have over here, right. So, what you can see over here is this node is going in the opposite direction. In other words, this is not a so-called feed forward cut set. Okay. So, once again to reiterate, what exactly is a cut set? It is a set of the edges in this graph, which if I remove those edges, will divide the graph completely into two independent subgraphs. Okay. Just to sort of complete this, there is E to F and F to B. Yeah. So, you can see that if over here if I remove all the red edges, right, the ABC part of it has edges in between the ABC portion, the DEF part has some edges that are in between the DEF nodes. Anything which is in between these two subgraphs or subsets has to go, is already part of this cut set that I have chosen for removal. Okay. So, that is number one, that is the definition of a cut set. It has to divide the overall graph into two completely disjoint portions. Okay. The second thing is, in this case for valid pipelining, I need it to be a feed forward cut set. Okay. Everything has to go in one direction. If I redraw the graph so that the direction of the edges is clear, all of them should go either from left to right or from right to left. Okay. So, this last one that I have over here, in other words, is an invalid pipelining. I cannot use this kind of approach, but as long as I can pick out a valid feed forward cut set, I can do pipelining on it. Okay. So, let us take this idea of pipelining one step further. By doing this, in other words, I was able to, yeah. So, this pipelining that we have shown over here, right, where we had the set of nodes, the BC, EC and EF edges are removed, right. It is sort of very clear even just by looking at it that this forms a cut set. It basically divides the graph into two portions, ABE on the left hand side and CFD on the right hand side, and anything which is going between these two sides has been removed as part of the cut set. Okay. And the critical path as a result has come down to 3. Okay. So, this was the first cut that we wanted. We were able to bring the critical path down to 3. What if I want to go further? What if I want to bring the critical path all the way down to, let us say, 1? Okay. How should I go about doing it? I can pretty much just repeat the process that I have discussed over here, right. So, what it would look like is every pair of nodes in this graph needs to have at least one register on the edge between them. Okay. So, how do I go about doing that? This is, for example, one valid cut set. So far so good, right. So, now these three edges BC, EC and EF have registers on them. Okay. I can go further and say add this. This is also a valid feed forward cut set. What it has done is basically taken A onto the left hand side, everything else onto the right, and anything connecting from A to the rest of the graph has a delay element, is part of the cut set and therefore has a delay element introduced on it. Okay. Similarly, I can do this. Looks good. Have I achieved what I wanted? Not yet. There is still this C to F edge, right. So, the critical path right now basically becomes the C to F edge, that is the node C followed by node F, each of which has a delay of 1 time unit. Therefore, total critical path is 2 time units. I want to reduce it to 1. Okay. So, if I want to do that, what will happen? I need to essentially introduce this register somewhere here, but now I have to make sure that it is a complete feed forward cut set, right. I also, and I can choose this as an example of a valid feed forward cut set. Okay. So, CD, CF, EF, is a valid feed forward cut set. If you redraw it, you will see that everything goes from the left hand side because A, B, C and E are on the left, D and F are on the right. All these three edges C, D, C, F and E, F cross over from left to right. Okay, so it is a valid feed forward cut set. And by doing this, I have now managed to introduce at least one register on every edge. The important thing is that it is at least one, because if I look at both of these, right, they both have two registers introduced on them, and that is important. Just the fact that I introduced a register over there for doing an earlier pipelining is not sufficient. If I also want to break the C to F edge, right, I still need to pick out a separate, I need to look at the original graph and pick out a whole new set of edges and once again do the entire cut set part of it for them. Just the fact that while I was pipelining the BC, EC, EF, right, I introduced a register on the EF edge is not sufficient. If I want to break C to F, I need to introduce one more register on EF. Okay. So, it is possible that I end up with multiple different registers to be introduced on a single edge. What is happening? They essentially just end up acting as a shift register. All that is happening is on one clock cycle the data goes from the source, that is E, into one of the registers. On the next clock cycle it goes from that register to the next register, and on the third clock cycle it goes from that register to F, where the computation is done. Okay. So, in other words, some of these registers are just sort of placeholders. They are holding data for some time until they are ready to be accepted by the next stage, and making sure that the path delays, the number of registers on every path when I go from input to output, are the same. Okay. So, once I have done this, I will end up effectively with a critical path which is equal to 1 in this case, after all of these registers have been added. So, in general, that is all there is to it.